Hey everyone, and welcome to The Explainer. Today, we're moving way beyond your basic chatbots. We're going to look at how to architect something infinitely more powerful, highly efficient, durable memory and caching systems for production-ready, autonomous AI agents. If you've been banging your head against the wall wondering how to make your agents actually remember things without absolutely bankrupting yourself on compute costs, you are in exactly the right place. So let's dive right in.
You know, it's super easy to just assume that if you throw a vector database at a large language model, you've somehow magically given it a memory. But if you've ever built basic RAG, retrieval augmented generation, you know what actually happens in the real world. The agent works okay for a little bit, but eventually it forgets user preferences, it starts repeating itself, it completely loses track of the ongoing workflow. And why does that happen? Because a vector database is really just a search engine. It's not a true memory system.
I absolutely love this quote from cloud architect Jeremy Daly because it perfectly captures the paradigm shift we need to make here. RAG helps a model look things up. A memory system helps an application remember. It's a huge distinction. Retrieval just finds static information from the past. True memory systems, on the other hand, provide multi-turn continuity across entirely different sessions and interactions.
Think about the painful latency tax you pay with a traditional stateless architecture. Every single time an agent takes a step, it has to send its entire context back to the model. That means it's rereading thousands of tokens. We're talking system instructions, complex tool definitions, action history, literally from scratch for every single turn. This creates massive, compounding token bills, and honestly, it just bogs the whole system down.
So we really have to move away from the old way of doing things. Basic RAG is all about transient, context-free vector retrieval. It's just a blind lookup. The new paradigm we are aiming for is built on durable, stateful memory systems. This is all about continuity. It's an architecture that learns, adapts, and actually reuses what it observes, instead of just passively searching through a pile of data.
Here is our blueprint for today. We're going to cover 1. The limits of basic RAG. 2. The shift from stateless to stateful. 3. Redefining memory as a write path. 4. The 5 memory types. And 5. How to efficiently reassemble context on every turn.
All right, let's kick things off with Section 1, the limits of basic RAG. As we touched on a second ago, pure retrieval architectures totally fail at resumability. Like when a user closes a tab on Friday and comes back on Monday, the agent is clueless. They fail at recalling user preferences, and they just break down during long conversations. Imagine a researcher tasked with writing a report based on a massive 500-page legal document. Now imagine forcing that researcher to reread that entire 500-page document every single time they want to write just one new sentence, right? The cognitive overhead would be impossible. Well, without prompt caching and a real memory layer, that is exactly what we're asking our AI agents to do. Recomputing these tokens creates massive overhead.
Moving right along to Section 2, from stateless to stateful.
We are fundamentally shifting from stateless text completions to stateful decision systems. By caching the process state of static prompts, we give the agent a working memory. But there's a catch. Notice the action boundary. This is the dividing line separating internal cognitive processes from external mutations. Caching natural language explanations or summaries, that's totally fine. It's safe to cache. But caching operations that trigger live tool calls or change a database state, that is highly unsafe. If you cache and replay those, you risk unauthorized or duplicate actions. You absolutely have to establish a strict response fingerprint to keep your system safe.
Which brings us to Section 3, memory as a write path.
Now, this requires a massive mental shift. Basic RAG is an upstream read path. Nothing the model does ever flows back into the corpus. True memory, however, is a downstream write path. Anything the system observes or confirms gets promoted to a durable store to be reused later. And this operational frame is absolutely crucial. You retrieve when you need knowledge. You store when you need continuity. You structure when you need precision, you summarize for compression, and you govern for production trust. Context shouldn't just be blindly stuffed into a prompt until it literally bursts. It has to be structured and compressed.
Next up, Section 4, the 5 memory types.
Okay, throwing every single observation into one giant catch-all vector index is a terrible idea. It causes context poisoning. Your agent won't be able to tell a strict corporate policy from a random passing remark. To avoid this, we have to structurally separate our schemas. Policy and preference memory? Those need exact match database lookups, their hard rules and settings. You definitely don't want semantic similarity when you're enforcing a strict refund threshold. You want the exact rule. On the flip side, fact and episodic memory rely on hybrid search, fusing both lexical and semantic vector retrieval to find conceptually relevant knowledge.
Let's break these down just a bit further. Policy memory holds your procedural rules. Preference memory holds stable user settings like, hey, always output in JSON. Fact memory stores durable assertions about the world. Episodic memory holds structured summaries of completed tasks, so the agent doesn't have to rederive solutions from scratch every time. And finally, trace memory. Trace is just the raw append-only event log. It's your flight recorder. You don't use the trace to find out what a user is like, you extract from the trace to build your facts and episodes.
But how do things actually get from that raw trace log into durable fact memory? Enter the promotion gate. This is your critical firewall. If your agent records every single conversational turn directly to long-term memory, the store is going to poison itself with hallucinations and repetitive filler. The promotion gate steps in, evaluates those short-term traces, extracts only the validated structured facts, and then securely writes those to long-term storage.
And finally, Section 5, reassembling context every turn. Now that we have this typed memory set up, we use a memory manager to run a fixed loop sequence. This orchestrates exactly what enters the LLM's context window. Step 1, append the new user message. Step 2, reassemble the prompt entirely from scratch using your typed memory. Step 3, call the model. Step 4, append the response. And Step 5, extract artifacts for the promotion gate. By doing it this way, we keep the static policies in the front of the prompt, maximizing those sweet cache hits, while dynamically injecting relevant episodic facts right at the tail end.
The key takeaway here is huge. Reassembling stays bounded, but accumulating grows forever. By reassembling a prompt from scratch using typed memory, you completely dodge the compounding token bloat. You also avoid that infamous lost-in-the-middle problem, where models just forget things that get buried deep inside massive accumulated chat histories. Now let's look at how we push this efficiency to the absolute extreme, especially for resource-constrained environments like mobile or edge devices. This is the ARC framework, the Agent RAG cache. It actively manages a dynamic, highly relevant cache of documents right where you need it. It uses something called distance rank frequency to measure historical demand, and hubness scores to identify geometrically central items in the embedding space.
And get this, the results of this intelligent caching are mind-blowing. The ARC framework drops storage requirements to a staggering 0.015% of the original corpus. That shrinks the cache footprint to practically nothing, while somehow still maintaining up to a 79.8% has-answer rate. It's wild.
Because the cache is so compact and hyper-relevant, it drastically reduces the need for the agent to make off-device remote calls to massive databases. And that slashes average retrieval latency by 80%, faster, cheaper, and infinitely more capable. That, right there, is the power of a proper caching and memory strategy. Well, we've covered a ton of ground today, from the action boundary to the promotion gate. But I want to leave you with this final, really powerful thought. Models are shared. The memory system is yours. Think about it. Right now, basically everyone has access to the exact same foundational LLMs. The model itself is just a commodity, but a well-architected, typed memory system that learns, adapts, and efficiently caches your specific organizational knowledge. That is your true proprietary moat. So, what do you think? Are you just building a chatbot that looks things up, or are you architecting an agent that truly remembers?